Mr. Lyden. How you doing there?
I'm all right.
So you want to? Are you going to present anything? I didn't think you were.
No,
You're
I'm
just
going
gonna
to talk about what I have, and people can look up the patents, and
All right. So
that's probably the easiest thing for them.
I'm gonna spotlight you for everybody, so everybody can look at your pretty face. There you go.
Okay, so you ready?
Yep.
Well, I got interested in computers because my son plays video games. Too many video games drives me nuts a little bit, but he invented some things having to do with video games, so that was good. Got some patents. And I was helping him build a computer, just a conventional computer, and got me a bit interested in, well, how do they really work? And I've invented a lot of things in my lifetime, over 60 patents. I hadn't done anything in computing. But when I looked at it, I found out what I think some of you probably know, but I'm going to present this in such a way that if somebody doesn't know anything about computers, they'd see what I was talking about, I guess. So the computers that you're using right now, they're called conventional computers. They also call them classical computers. They use the digital system, the binary digital system, ones and zeros, to represent data. It's how they process data. It's how they store data. And they do that because they're dependent on transistors. And you can kind of think of a transistor as kind of like your wall switch. You know, it's got two positions, 1 and 0. That's a little bit oversimplified, but so they can be switched one way or the other to store or represent 1 or 0. And so all information on computers is turned into ones and zeros, and that's how it's stored. That's how it's manipulated. Now, when they do that, to create a 1 or a 0, they basically send a square wave. A square wave just looks square, looks like a column. And a tall one is a 1, and a short one, or non-existent one in some cases, is a 0. And when they send the information, the ones and zeros, they have to be sent in a series, one after the other. And right now, with the kind of encoding that we have for things, if you want to say the letter A, you have to send 8 ones and zeros in a series, one right after the other, to basically communicate A. So you've got to send 8 things, and each one takes time in a series. You can't send the ones and zeros in parallel all at once. It takes time. And to create those square waves, what they have to do, basically they're switching on and off, usually a couple capacitors and sometimes more than that. Maybe there's a diode and a resistor in there. But the bottom line is, to create those ones and zeros, they're using wires. Wires have resistance, they're metal. And the switching burns a lot of energy. So now as we try to make bigger computers, faster computers, quantum computers, the amount of energy goes up kind of astronomically. And that's why right now there's a crisis. Everybody thinks we need AI and artificial intelligence and these supercomputers, and they want to build these huge data centers, and then they don't have enough energy for the huge data centers, and they want to build more nuclear reactors or whatever. They're going to need energy from somewhere, because basically they've painted themselves in a corner using the digital system. And I think my opinion is that these things they're wanting to create within a few years are going to be a bunch of white elephants and worthless. This is where optical or photonic computing comes in. Instead of representing the letter A by saying 8 ones and zeros in a series, you can use the visible or invisible, for example, light spectrum, and say the color blue at 472 nanometers means A. So if I send the color blue through optical fiber cable, that says A, and it says A in, well, the wave period on through most of the color spectrum, one period is about 2 femtoseconds, and maybe you have to send 10 of them, or maybe you send 100 of them so you can read it really well and it doesn't take up a lot of bandwidth. But the bottom line is you can send the letter A with light really, really fast, more than 1,000 times faster than you can send just a single 1 or a 0. And you've got to send 8 of them, and you've got to wait and send them one after the other. So with optical computing, you can basically send, the easy way to think about it is different colors represent different letters of the alphabet, numbers, or symbols. And my first patent, and I'll give you the number and you could read it if you like, but I would just look at the claims. It's US 11809839. And if you look at claim 1, what it basically says is using sinusoidal waveforms, light of visible or invisible light, to directly encode letters, words, numbers, or symbols. That's what it says. It's very broad. It's what you call a foundational patent for optical computing, photonic computing. So that's claim 1. One of the other things I figured out to do.
Rob, real quick, as Eugene. So
yep.
Before you go past this, how do you sequence the letters? So you're sending 8-bit characters one after the other. How do you know that the A comes before the L?
Right. The beauty of it is you can send them in a sequence, but with optical computing, you don't have to. You can send it all in parallel, all at once. You can send all these letters, all these numbers, all at once, and it comes through, and you can tell what colors are there. You can tell what data is there. And you can do that because there's things called fast Fourier transform that can manipulate it and tell you what's there. You can also, one of the things people don't recognize sometimes is that a Fourier device is like your glasses. A lens or a prism is a Fourier device. You can take light that has a bunch of different elements of light or spectrum there, and it can take it and break it apart and scatter it, and you can see exactly what's there. So the beauty of optical computing is it's parallel processing. You can do it in series like digital, makes it slower, but it's still faster even when it's slower. But it is so much more faster because you can send it all at once, bing, just like that. And this relates to the thing I was going to talk about next. I think it's claim 16 in the patent. I basically figured out if you want to send like a huge number, right now you can either do it digitally and it's a long string of ones and zeros. But with optical computing, you can encode, you really have numbers 0 through 9 and then, it repeats kind of, it depends on what place they're in. So if you got 0 and 9 encoded, you can send one wavelength to represent whether it's 1 or 2, and you send another one as a pair, related pair that says what the placeholder value of that number is. If it's 2, or is it 20, or is it 200, or 2 billion? So it's basically showing the placeholder value or the exponent value. So if you send those two pieces of information, you know what 2 is. It's just number 2. Is it 2 billion? And so you can take a huge number, send it each digit, each base number with its corresponding placeholder value. You can send it all at once like this. It all goes. And you immediately have the big number. You know exactly what it is. So you can send large numbers basically almost instantaneously, very little processing time. And because you're using optics, you're not using wires. There's no resistance. There's no switching, going on there like there is when you're trying to produce square waves.
Right.
So that's one of the things you can do.
We got 3 questions already.
Okay.
For you, and now
Sure.
4. And, okay. All right, so we'll run them in order. Nick, go ahead.
Yeah, hi, Robert. I can understand letters and things like that, but when you say we're doing the video that's showing you right now, how is it tabulating all of that video at the light wave compared to digital.
Right. Well, that's optical. I mean, you're looking at something optical that's actually been turned into digital, and then it's turned into optical again to fly through the optical fiber cables between us, and then it's converted back to digital so your computer can do it, and then it appears as optical. So, right now what's happening is you're taking an optical device or analog, you're turning it into digital, then you turn it into analog again, and you're sending it through fiber cables. Then you got to reconvert it back, and that takes a tremendous amount of time and energy. I mean, for us, it's very quick, but relatively speaking, it's very slow and very energy efficient. And you can take an optical lens, put it to optical fiber, and you can send images. I mean, you can send a real image in real time optically without digitizing it. It's just that
on the back end, you wouldn't be redigitizing it like on my phone. It would be typically.
You'd have an optical computer. Eventually, you'll have an optical phone, and it won't have to necessarily break it down into digital. Now, digital can do some good things, and I think it's been with us a long time, and this is going to integrate with digital, and digital will probably stay for certain things, but most of the traffic on the internet is videos and images and things as far as the volume. And so if you can go to optical and go from literally camera to optical fiber and piping the optical fiber and coming out in the other end, that's a much more efficient way to do it. And some of the things I'll get into next have to do, well, how do you put that in memory and this and that, and how should a brain really be a brain for an optical computer be, so to speak? How does it store things? How does it process things? And I'll get into that in just a little bit.
Okay. So we got a lot of questions here. We'll go to Kavita next. Yeah. Oh, yeah. We knew we would.
Thank you. So can you speak a little bit about how you decode it? Like, as in the receiver will have to, the person who receives it will have to have some sort of a key, which allows you to tell them.
No, you don't need the key. The funny thing is, I think the patents I'm getting are in some way kind of analogous to the RSA patents that everybody used, because they use keys and security keys and so on. The thing about analog is not, I mean, it's not really hackable. I mean, digital you can hack. Analog, you can't really hack. And although people say it's impossible, I think, impossible things just take a little longer, But there's things in the patent about how to use cryptography to make this also unhackable. So bottom line is, you don't need a special key or anything. If you want it to be secure, you can do that. But it wouldn't be using some of the old forms of encryption. It would be using things more like elliptical and things that frankly only appear in my patent, that people haven't thought about to do. So does that kind of answer that without getting too hairy about it?
Well, even without having to worry about whether it can be hacked, actually, how does the receiver know how to interpret it?
Well, if you got optical computers and your encoding says light of this frequency means this, both the computers know that, and they know they can read it. And you can read the light, and it says, oh, it's 472. That means the letter A. It recognizes that.
Yeah, but what I think she's asking is like you're doing with the numbers. So you send two things. You send a 2 and you say that this is,
right.
This is 1 billion, and you send a 1 and you say this is 100 million.
Mm-hmm.
How do you order the characters? Is there a way to? Are you doing the same thing to order that? If I spell your name Rob, ROB, how do I send them in parallel and order them properly?
With numbers, with numbers. It's not maybe intuitive to you off the top of the head, but they self-assemble basically. If you've got 1, to the times 10 to the 3, and you got 2 times 10 to the 4, and that's the way the information comes in. They all go to the right spot. I mean, that's just a matter of software, and it recognizes what
how do you
those
do
are,
that with letters?
and they self-assemble. A 10 to the 3, a 10 to the 4 is here, and so the software would be able to crunch that pretty easily.
Now, how do you do that with a letter then? How do you send your name, Rob, R-O-B, in parallel and have the receiver put the letters in the proper order?
There's a couple different ways you can do it, and I can't speak to all of that right now because of patent reasons. But one of the ways that people aren't used to thinking about, if you're talking an optical computer, it sees your name, Robert Lyden. It captures the image. It sends the entire image. And it can send, a whole page of text. So with optical computing, with some forms of it, you can break it down into individual pieces, individual letters, but it can also capture entire words, entire paragraphs, and send it and store it holographically. And that's kind of getting into the data storage memory side here, which I'll like to get to.
Okay. Kavita, did that answer your question?
Kind of, maybe.
Yeah.
Okay. All right. Thank you. So Alan, go ahead, sir.
Oh, I was going to expand on that. I was kind of confused how you're receiving the light. Are you using a photocell? Are you?
Well, you can use photocells. There's a whole bunch of optical devices that are out there that can both create the light, send it, receive it, and interpret it and know what it is. That's kind of getting down in the weeds, and I kind of don't want to go there. But there's plenty of devices around that can do that stuff.
The thing about it is that, Verizon has fiber optic cable, and it uses lasers to transmit information and stuff.
Yep.
And even then, it still uses mirrors, and it needs some sort of amplifying device in order to. Because you still have light always has a 1 over r squared deterioration. So you're not going to have the original waveform every time you go down at a certain distance. Okay, it will deteriorate. So how are you going to amplify that? How are you going to?
Well,
how do you maintain fidelity over?
Those systems already exist for sending light through optical fiber cables. You don't have to recreate those. Yes, they know how to amplify them, how to send them across oceans. We don't have to reinvent that. The funny thing is that the optical fiber cables out there and the connections and all that all exists. What hasn't been put together is, okay, let's have an optical computer or a photonic computer. That's the part that some people are now trying to do and doing. And that's very doable right now. I think all the components to make an optical computer are there, with one exception where things aren't as good as they could be or should be. And that has to do with the optical memory and processing. And that's why my third patent has diagrams and discussion about that, which I'd like to get to, what that looks like. What does a hybrid optical memory and computing chip look like? And how would it work, and why would it be that way? And it's pretty easy to explain, and maybe I can get to it after this next, maybe last question.
Yeah. I think, we got 3 lined up here, so we'll go with, so the next one I'm going to go with is June Lee. Are you able to unmute and ask your question?
Oh yeah, I'm just wondering. I know a large company like NVIDIA is already kind of putting in implementation for the photonic chips and using in the computing. I'm just wondering, what is new here, and are we going to build new companies? And
well, I can explain that. Basically, when I filed the first patent was back in 2022, and back then I thought, gee, am I crazy or am I the only person to see this? But then in the last 3 years, everybody's coming along. Everybody suddenly wants to do optics and photonics, and they're coming along and they're making pieces of hardware. Some people are trying to make and are making logic chips. There's already optical neural networks being made. A company called Qont in Germany's doing that, and there's a couple others. I mean, I know who they are in the United States. I've cited them and all their relevant patents on my patents, and they're coming along. But the truth is, all the big companies kind of blew it. I'll just say it straight out. In my opinion, NVIDIA, IBM, all these big companies have been so heavily invested in the digital system, thinking digitally. I mean, right now, all these quantum computers they want to build, it's all based on digital, and it's the wrong path. It's a path that requires so much energy. It's not really doable. You can't, if you got to represent things with 8 digits that got to go in a series, you're never going to get to where you really need to get to go. And they're all banking on this because that's the kind of chips they make. That's their manufacturing is all based on that. They'd have to change so much. So I think they've been late to recognize where things go. At the same time, they're making good moves, but not as strongly as I think they should. And I think these billions of dollars that are slated to build these data centers based on digital computing methods are going to be a terrible waste. So I'll just stop there. So they're doing some things, but the funny thing is, it was ironic. I was visiting my son, and I was staying at a rest area outside Portland to do it. I needed to save money at the time, so I was going to sleep the night in my car when my patent attorney called and said, "Well, you got the claims for your first patent," and I had to kind of sit there and laugh. It's like only in America, that some guy gets foundational claims on optical computing that NVIDIA and IBM and all the rest of them didn't get and didn't think about. And so I think a lot of people are going to want the patent and be able to use it and license it. And kind of my question is, what's the best thing for me to do with that? So yes, other people are getting with optical computing. The funny thing is, if they want to do it right now, they can send digital stuff optically, but the minute they want to directly encode something, instead of saying 8 1s and 0s to say A, they just want to send the light that says, "Hey, this is A."
Yeah.
That's my patents and what I'm doing.
Yeah, I think I look at the photonic computing like back in 2017. So this is I think people are considering this a long time ago, and it has been progressing slowly.
Yeah.
I look at the several university, large university all have this research, and that time the problem is all of our devices are built digitally, so you can't have a computing device actually worked without a proper converter converting from digital to analog and back and forth, right? So that has been a big challenges, and I think recent years, because the Moore's law is not going to scale properly, continue to scale in the digital, so people are actually making actually quite a progress there, but like you said, if we probably in the future will need like a photonic computing native device, but things will have to happen gradually. I think even the manufacturer itself is quite a challenge because how do you scale the optics to I think one of the big problems is the error code, right? So because the light is our own analog, and if anything downs wrong, you don't get the correct result. So
there's ways to deal with the error issue, and I can get to that. So yeah, people have thought about photonic computing for a long time. I think Alexander Graham Bell.
Before you go into that, Rob, I wanted to add a comment here. So, one of the reasons that I wanted to have Rob on here, because I think it's quantum is coming, but Rob has what I consider to be an obscure solution that really nobody has considered, and it's very possible that this solution could be implemented sooner than quantum could be implemented. And that's why I brought him on here. And that's really what we wanted to see how things are going.
Well,
and to get people's inputs. But I have more questions here I want to get to.
Yeah, I'd like to not get too much into the weeds and kind of move on a little bit, because I think this is the only way quantum really can be done, at least effectively. But
okay, go ahead then.
Yeah, people have looked at doing photonic things, but for reasons I can't explain why people didn't do what I did, but they didn't, and they hadn't figured out that they were so hung up on digital. They hadn't figured out that you can actually drop digital as a way of encoding things and representing things. You can actually do it an entirely different way, and if you look at it that entirely different way, a lot of these problems just go away. Even this idea of quantum computers, and you hear this stuff about, superposition and such, and entanglement, and what they're really trying to do. Most of the present efforts, it's kind of nonsense, quite frankly. They're talking about doing these things, and what they're really trying to do is make digital capable of parallel processing. When you strip away the superposition and the entanglement, they're really just trying to make your conventional computer that we have here be able to do parallel processing. And right now, when they do what they're trying to do, they'll send in a horizontal axis, let's call it a 1 or 0, and in phase shifted, they'll send another one at a horizontal, and they're trying to create these extremely low temperatures and all this kind of stuff, so that when they know where the one point is on one, they know where the other point on that is, and they can know a couple things at once. Well, the truth of it is that light, if you take light from a single source, and it has multiple, it's not just one frequency and wavelength, it's multiple frequencies and wavelengths of light from a single source, and especially if it passes through a lens or something, it's already entangled. It already has superposition. And you don't have to create digital entanglement and superposition. So I think the direction they're going is it's hung up on digital, and because that's the way they've been making things, and that's how their fabs are and their factories are. But I think they need to step away from the whole thing. They've kind of painted themselves in a corner and take a different approach and make a different kind of computer. So, so my first patent basically taught those things I just mentioned. It also teaches using that you can, and this is totally different, you can represent all numbers and data using just prime numbers, and actually only a few prime numbers, and their squares and manipulation of them by multiplication or addition. So that relates to something else. It could be used for breaking the kind of codes we have today. The other big thing, I guess, that's in the first patent is, most of you know something about how DNA is in the human body. That there's 4 different pieces that are combined in different segments in a series to create DNA and store information. Well, I basically taught in that first patent that you can do the same thing with light. Just think of the 4 pieces, let's say, being 4 different colors, and which ones you combine, which ones you put in what series. There's your data. And so I call it DNA color coding, not terribly creative on the word, but you could have pairs or 4 or 8 colors. I'll say colors instead of frequencies and wavelengths because people can visualize colors. You can combine sets of those and put them in a series and basically create trillions of data points. Right now I think standard code is something over 1 million, maybe 1.5 million. So you could have trillions of data points by manipulating light. So those are the things that are in the first patent. And the second patent is a continuation, has different claims. And it basically says the same thing as the first one, but it says and or square waves. So basically it's saying, yes, you can do this photonic stuff, but you can also talk back and forth to conventional computers like we have here, which use square waves. And the third one says about the same thing, but you can also use pulses and wavelets to encode your information. So you've got sinusoidal waves, you've got pulses like Gaussian pulses, you have wavelets, which are kind of like a little jiggle, kind of in between sinusoidal and a pulse. And these are different ways that you can encode information. So that's what's in the first 3. And then the fourth one is where I addressed how would a photonic computer chip or brain look like? How would you store the information? What would you ideally like to have? And we're all sitting here and we're all using our brains, right? We can see things. We have data input from our eyes. We can hear. We can touch. So we have multiple data coming into us. That's just the normal human condition. And that's parallel processing. We're not just looking and then we got to hear and switching from one to the other. We can do it all at once. The truth is humans are the best quantum computers in the world. And the brain, I think, actually does do quantum computing, and Roger Penrose, I think, says this. So you want to create a computer that you have data. A lot of data streams are coming in simultaneously. And what I showed in a diagram, it's 41, and the pending patent that I have, and I'll give you the number, serial number. You can maybe look it up. I don't know if it's published right now, but it's,
yeah, I can provide all that information.
Yeah, it's serial number 19025386. So basically what I've got there is I got a chip and it says, okay, we have an optical fiber connection, let's say, or a waveguide, brings the data in. And it brings the data into a, let's call it a multiplexer or a demultiplexer. It's an optical device that can manipulate the light. And it's in kind of like a turret on a battleship. And that turret sits in the middle of an array of optical storage medium. So think of it as like a stop sign. Let's say it's 8-sided. It doesn't have to be 8. Let's say you have a turret, like on a battleship, sitting on the interior of a octagonal shape structure, and that structure contains optical storage medium, crystalline material, like lithium niobate or glass, or not glass, but so you basically got an optical storage medium, and you got this turret, and this turret has as many sides and as many, let's call them guns, but they'd be lasers. You'd be doing, let's say, holographic storage. So you got this 8-sided thing with 8 little guns that shoot out and can store information simultaneously in these 8 sections, which could be one piece of material, but 8 portions. So that data can come in just like we're doing right now. And what happens to the brain? Well, our hearing things goes to like a hearing spot in the brain, and our this goes to the optical part. It's in the back of the brain. So the brain has different sections for doing different things well. And so you kind of want to recreate that in a way. I mean, nature's pretty smart. Figured this out a long time ago. So you have your data come in. The data can go to, let's say, 8 sections. It can be stored in each one of those 8 sections, or the data can be retrieved from any one of those sections, and it can all go on at the same time. So you don't want to just go in and store in one little block, one little holographic thing. You want a bunch of them, and you want to be able to do it simultaneously so you can read and write and retrieve information at the same time. So that kind of handles kind of the optical memory portion, let's say. Now, each one of those things in turn should be, and I explain, because this is what our brains do, it's linked to a neural network, or it's linked to logic chips that can do processing. So you've got your storage, and the storage is basically built right on top of, here's your storage, coming in, and here's your processing, and they talk directly to one another. So you can have your neural network and optical chips come off of each one of those in the holographic storage portions, and they can all talk to one another too, because that's what the brain does. We bring things in, we can put things in memory, and then we can think about it and we can process it. So in my view, if you want to create artificial intelligence, I think St. Thomas said something like this once, that grace does not abolish nature, but perfects it. I think human brains are the way they are because they work pretty well. And if they didn't work well, we wouldn't be here. So you kind of want to imitate nature in a way to create, let's say, the memory and the processing storage part of it. And so the last patent I filed basically shows this and teaches us. It says, should be kind of like this, and it could be like this, and you wouldn't need to have just one holographic thing. You could have a bunch of them, and they can all be cross-talking to one another and all be hooked up to neural networks that already exist and logic chips that already exist. And I think that's probably the best approach to it. Otherwise, right now, there are optical ways of storing optical information. It can be done on film, it can be done on tape, it can be done in DVDs and laser discs. But most of that's been done, well, a lot of it anyway, has been done using digital, and they burn basically ones and zeros into a substrate that's on like a DVD. I think there's better ways of doing it. So that's kind of a lot to kind of throw at you, but
yeah,
that patent does that. Go ahead.
Yeah, no, it's Eugene. It is a lot, and thinking about how it goes. This is the first time that we've done a presentation based solely on patents, and
right.
And and I hate to say it, but I think I've kind of done everybody a disservice by not providing the patents ahead of time for them to be able to review and have a better understanding. And and I think I'd like to get to some of these questions before we run out of time. But
how much time do we have left, Eugene?
10 minutes. So
okay.
But I want to bring you back. So what I want to do is,
I guess I'd like to say one more thing, and then I can take some questions if that's okay.
That works.
Because I'll get through the big part. So the other thing that I figured out, and this has to do with sending information. Right now, when they send information through optical fiber cable, they use something called constellation patterns or diagrams. And it's things like QAM and quad, and most of you probably wouldn't know. But basically, they send the ones and zeros in quadrants, and they can pack them. They can use different amplitudes and different phase shifting to basically send a bunch of ones and zeros through fiber optic cable, okay? One of the things that I realized is that if you apply that sort of idea or technique, constellations, to optical computing, instead of sending like 8 ones and zeros to be able to say A, you send one thing and it says A, And you can send, so you can send a lot more. You can pack a lot more through an optical fiber cable just by the fact that you're not having to send so much. The other thing is that, and this would be kind of hard to visualize, but if you send the number 2 using the correct color for 2, but if you also send it in the correct location, a single dot, if you have like an archery target, and if you designate that the inner ring at this position is 2, it means 2. Now, if you're sending light that's encoded to mean 2, and you're also sending it at the correct spot that means 2, you have kind of a double, you have a redundancy there. You're sending 2 with the correct light wavelength and frequency, but you're also sending 2 at the correct position in the constellation. And so you've got kind of error correction or confirmation that the information is correct and free of errors, because they should jive. And if they don't jive, you know you got an issue. So I'll stop there and try to answer some questions if I can.
All right. Yeah. So what I'd like to do is talk with you after this. Find a time where you can come back on. Then what we'll do is we'll send the patents along with the invites so that people can review the patents. And I think it would serve everybody better with that. If anybody has any comments, you can put them in the chat and let me know about ideas and how that sounds. But let's go. So Dave M, you're up.
Sure. So first of all, I like the whole concept. The whole idea of digital zeros and ones is just about the existence of a signal or not, basically, that you're talking about. Now you're talking about a whole lot more resolution and capability with light. So I get it. It makes sense. You can get things through faster. But the challenges that I see are, first of all, what's the maturity? Knowing that in order to have a whole system that's working, you have to look at the maturity of the least mature of the components that you have to build out in order to have a functioning system. So what TRL would you put this at? And how do you build this infrastructure and have a business model against this, right? Because you were talking about massively changing all the infrastructure that exists, except for maybe the fiber optic itself, right? The transmission part of it. But, all the compute, you're talking about radically changing. So how do you build a business model out for that?
Well, I don't feel that I need to build the business model. I frankly think there's too many computer companies in existence right now. And I think some of them need to change their focus and start spending more time and energy on photonic computing. I don't have a desire to launch the next Apple and be a computer.
No, I'm not saying you. I'm saying it. I mean, but what you need to. But just my opinion is, first of all, what is the readiness? What's your technology readiness level, right? Of the lowest,
I can
the lowest mature
that.
components in the system, because you're going to need to know that in order to know the investment. In order to say, this is worthwhile, it's a worthwhile investment to build all this out. Because if there's no business model, I'm not saying you have to do it, but if there's no business model behind what you're talking about, it's going to be hard for people to, to engage.
Let me explain. There are people who already have made the optical neural networks, and there's people who've already made the optical logic chips. And there's several people around the world building optical computers as we speak. So they're doing it. It's happening right now. And some of it that I'm aware of tends to be more over in Europe than it is here in the United States, which is kind of troubling to me. And frankly, there's a video which I'll send to Eugene, and there's no hard data in the video, but the video was it's on YouTube, overheard people in China. And the people in China were talking about our desire to build these big data centers and based on digital. And they were basically saying, we're working on things having to do with optical, and in 3 years, we'll be launched. We'll have it out there in 3 years, and those silly Americans, they're screwed. So whether that's true or not, I can show you the video and you can listen to the fellow and the conversation that he heard and had, but I wouldn't doubt it. I don't know what the Chinese are doing in some secret lab somewhere, but it would not surprise me that they are ahead of us, and by a long ways. I think some of the Europeans, I think QAnt with their neural network, you take that piece, you put it together with a couple other pieces, some of the logic chips that are being made. I think NVIDIA has the interconnects and the ability. I mean, Jensen stood up over a year ago and he held something that looked almost like a guitar or a piano guitar that said, well, this can carry all, this is an optical device and it can carry all the data on the entire internet. Boom, right in his hands. So the pieces are there. Whether some people in labs in this country, unbeknownst to all of us, are working on putting those pieces together and how far along they are, I don't know, and we can't know. Whether the Chinese are that far ahead of us wouldn't surprise me.
Yeah.
Some of the Europeans seem to be ahead of us. I mean, I could name the companies, and frankly, the companies I'm aware of, they're named in the patents, and you can look at their patents and see where it's at. So it's happening right now. Who's going to be the first to have the best? I don't really know. I guess my contribution is I figured out what the coding should be like, and I figured out how to represent numbers and how to create trillions of data points and what the brain should look like in an optical memory and compute device. Those would be my main contributions. And there may be a company out there that, if they become aware of my patents, will say, this guy has this. We want this yesterday. So I don't know how it's going to all shake out. I can only control what I can do and say. And anything I find out ends up in a patent and reported to the patent office. And that's kind of what happens there. And then I get what claims I can get and teach. Patents are teachings, and I'm trying to teach the best way I know how to do this. But it's like making a movie. You can write the screenplay. Takes a lot of other people to make a movie. Yeah. It's a team thing.
Yeah. So Dave, I suggest that that you and Rob get together, because we're starting to get into the weeds on this one, and I think I can kind of see where you're going. There needs to be a consortium of effort behind this.
Yeah.
Right.
I mean,
yeah.
I mean, it makes sense. It makes perfect sense. And I get
it does. No, it did to me
people
too.
Advancing technologies all around the world, but you kind of need to know where to jump onto the roller coaster ride. You know what I mean? So
I can tell you pretty quickly which people I would, if I were to be the czar of this for a day, I could tell you which people I would get and what technologies I would get to put it together pretty quickly if
knew
somebody who wanted to do that. So
we don't want to put that out here yet.
Okay, we won't.
Yeah.
Thank you, guys.
All right. Thank you, Dave. Nick, you were next.
Yeah, you touched briefly on error correction. If I spell Eugene incorrectly,
I can't hear you quite. Could you speak louder? Maybe it's.
I'm sorry.
It's not your fault. One of my speakers is out in my computer because I dropped it, so I only get one.
Yeah. You touched briefly on error correction. If I spelled Eugene incorrectly, would your brain be able to write back and say, correct my spelling?
Well, the brain exists right now on paper, so it's difficult to say that. But what I was communicating about the error correction is right now, when computers send a message, let's say there's usually a header, there's a kind of a start part that says this is a message, gives it kind of the thing, and then there's the payload, what they call, and then there's the footer, which is kind of like the end part. Mm-hmm. And when our computers that we use right now, they sometimes run the data multiple times to do error correction. 3 is not uncommon. So it's not just that you got to send the data once, you got to send it several times, and it kind of runs a comparison, and there's all kinds of error correction things out there, and we can't really go into it, and I don't know that I know it all or understand it all. But it takes a lot of time and energy to do error detection and correction. And what I was suggesting is that one of the things I realized is that when you send a message using light, and you're encoding, let's say, a certain color or frequency of light to, say, the letter A, as long as you have good resolution and you can see it, you send that color long enough so that it reduces the bandwidth you need to use to see it. And you send it long enough to where you're sure that it says what it says. But at the same time, as much as necessary, as little as possible is kind of what you want to get to. You don't want to spend more time and energy sending something if you can already read it accurately at a certain point. You want to stay within the desired accuracy you have to send it, and to send it as long as you need to send that waveform for you to be able to recognize that waveform. Well, that's 472 nanometers. That means this. And so that is part of, the error correction or getting information accurately thing that you want to do. The other thing that I recognize is that right now when they send information through fiber optic cable, it's done in constellation patterns. And you'll have to kind of, if you never heard about that, it's sent in constellation patterns where they basically phase shift the stuff so it forms like a circle or a circle within a circle within a circle, and they can send like hundreds of these points. But my point was, when you're doing it with digital, you're sending ones and zeros at those points, and you got to assemble 8 of them to get one piece of information. If you're sending light, well, each point of light is the point of information. And if you also send the light at the proper frequency at a location in that pattern that means the number 2, you're sending the light that means 2, but you're also sending it at the position that means 2. So you really know it means 2. And it kind of gives you a cross check on the information you're sending and whether it's accurate. That's the only thing I can say to that right now. It's just a different way of verifying information that's possible if you use light and if you use it in that way.
Yeah, so we're 3 minutes over. Just want to let everybody know. A couple questions that were in the chat. The people we never got to. Are there any
for Dan?
But they people dropped.
Okay. Any questions for Dan?
No, nothing new for Dan. But I want to reach out. So Todd Lesser, you unmuted for a second or two. Did you have a question or not? I'm not hearing anything from Todd.
No, he looks like he.
Okay. All right. So, Alan Holm.
Yes.
Go ahead, sir.
Just quick question. I'm not familiar with your patent, but for your patent, did you have to build a prototype? I mean, if you're going to do something very simple, okay, that answers my question. But if you're going to do something very simple,
no, you don't have to. You don't have to build a prototype to file patents. Okay, it's considered a reduction.
If I were going
to
do this, let's say I was going to do a science experiment, like for high school. I mean, if I were to say, let me say the word, send the message "Hello World" 10 feet, and encode "Hello World" using your color palette and send it over. Is it possible to actually do that? Send it over, and then just say, "Hey, this is the message that comes out on the other end, and it took this much time to do it."
Sure.
Okay, so you use something like some light spectrum analyzer or something like that?
There's existing laser equipment right now. There's things out there that can send, I'm aware of, over 200 different colors. Let's put it, I'll say colors. It can be in the ultraviolet spectrum too. There's equipment out right now that can send hundreds of different colors and you can discriminate them. You can see the peaks really clearly. Here's 472, here's 474. So you can send a pretty tight package of light, and as long as and it's not difficult, it's actually fairly inexpensive to perceive these on the other side. So you can send laser light different frequencies right now, and you can pick them up, and you can know that you've received them. That's pretty easy to do. That wouldn't take much time or effort for you to do, and I could tell people where to go shopping to buy that equipment. It's out there. Some of it's not real expensive, and so the answer is yeah, you could do it. You can definitely get yourself some lasers, and you can get yourself some. Basically, it's kind of like a spectrum analyzer, but they're simpler than that, and it'll tell you what's there, and you could communicate. And as long as you coded it the way you wanted it, that well, this color means this, or this color means an entire word. So you can send an entire word as a color. You don't have to say elephant. You could say elephant will be this color. Right. Boom, gone.
Yeah.
When our televisions came over the airways into an antenna, isn't that it's basically like television signal?
Television is it was originally analog, and that was Philo Farnsworth, and he was a remarkable guy. Towards the end of his life, he was working.
We don't want to get into the details
making
there.
Fusion, but anyway, it's a little different thing than television. But bottom line is, you can do it.
All right. So I'm going to put you and Dr. Holm together. Dr. Holm, I don't know if you looked in the chat, but Jim Best says hi, and hello, Jim. Good to have you here. All right, Kavita, you had a question.
Yes, I actually do have a question for Dan if he's still on.
I believe he is.
I'm still here.
Great. So we talked about how you're treating the surfaces with your, the laser technology addresses issues with water, but what about other atmospheric pollutants, like chemical-based pollutants? Like, how would you? Does this not help with that at all? Just wanted to get your thoughts on that.
Well, the most common questions for us are about water-based fluids and oil-based fluids. And repelling an oil-based fluid or an oil-based contaminant is a different texture than the one that I showed on screen. But we do have that texture. It's another copied from nature biomimetic texture for oil repellency. They look like arrays of mushrooms at different scales. So we're able to do oleophobicity and omniphobicity. And occasionally we get a request to do something specific for a specific foulant or a specific liquid, and we have to do some development work, but those two cover 90% of our use cases.
I see, but if it's some other hydrocarbons or some other material, some other substances, pollutants in the atmosphere, then this does not address that, right?
Perhaps not directly. We would have to test and see whether it only takes about a week to figure out which of our textures responds best. And the truth is that a lot of our customers don't really know some of the phenomena they're asking us to affect, but really trying it and trying it on an array of different textures is the easiest way to figure out where we should go next.
Thank you.
Yeah, I think Dan and Kavita, I think we need to get together and talk about that. Yeah, because that would be interesting about particulates. And, if I could get all the ketchup out of my ketchup bottle rather than leaving that little bit in there.
Yeah, no, ketchup is water-based. That's been proven. It's a super hydrophobic surface. It's been done. Yeah, sorry.
It would. Yeah. So you can address different viscosities, correct?
Yes, easily.
Yeah, because I drive my wife crazy because I got to empty every ounce into the next bottle, and she doesn't like all the mustard and ketchup and aloe bottles everywhere.
You can search for empty ketchup bottle with a super hydrophobic surface, and you'll find the YouTube videos that demonstrate it with a coating from a competitor of ours who we know well and we like. The only reason people haven't come to us for it is because at our scale, it's probably a little too expensive to put it in every ketchup bottle, but we're getting there.
Sounds good. All right. Anyone else? Brian, I
Rob,
saw
you
you
blew my
had your,
mind.
oh,
Go ahead.
Brian, you have a question. Brian, go ahead.
Hey,
You're muted, Brian.
oh, you're
I had
muted.
just
There.
a real quick question for Robert, and then I also have one for Dan. I've spent probably almost 1,000 hours looking to both of their patents and their products. I know quite a bit about it, and I would say that both presentations are greatly underselling the full capabilities and potentials, and I'm truly impressed. One thing I really am impressed with Robert's is the potential for being used as a video game engine for massive amounts of data, or for land navigation where you're analyzing billions of data points per second. I think there's a huge potential for that. And then with Dan's products, I think the oil and gas industry can save billions of dollars by retrofitting, cleaning, hardening, etching the interior petroleum pipelines.
Mm-hmm.
And I also think that the food and beverage industry is going to yield some significant results from that as well. That's my thoughts.
All right, thank you. Yeah, I kind of thought that we'd have more people here from the AI community for Rob's presentation, because a lot of number crunching to process all that data that AI is trying to do in their LLMs and stuff.
Yeah,
and I think it could be done faster. And like you said, the pieces are all out there. It's just nobody's taking the time to assemble them into a product yet. So that would be the ask, I guess. Here is that we're going to bring Rob. We're going to end up bringing, I think, Dan and Rob back on, and on separate calls to cover their solutions. And especially with Rob, I think we need to get your patents out there in front of people ahead of the call. So we can look.
I actually think it was probably okay like this, Eugene, because if you'd give them the patents are like 100 to 200 pages, and it's a really deep dive. And this way, they've kind of heard it. They've kind of hit the highlights, and when they go to read the patents, they know where it's going, and are probably a little more motivated, or it's easier for them to understand what the payoff is.
Yeah, but they're going to do the same thing I did. They're not going to read 300 pages of the patent. They're going to stuff it into an AI, and AI is going to print out a summary of about, I asked for 5-page summary.
Yeah.
So.
Well, I have that in a document called summary. It's like 2 pages, I think.
Yeah, that's the one I think I sent.
And so I can get you those, and you can give them to people who want to look at them, and that'll work.
All right. Yeah. So, but there are people out there, a lot of researchers, I'm sure. I worked at the Naval Research Laboratory, and I know how a lot of those people think and function, and they would actually take the time to read most of it, if not all of it.
Well, all the power to them.
Yeah,
it's probably easier to read than it was to write and research, but it's not that much easier.
All right, so we still got people here. Major, it's good to see you here. Kavita, thank you for all of your input.
Thank you so much. I enjoyed these.
And I do have, you did put your email in there?
I believe I did, yes.
Okay, so so I can connect you with everybody.
Amazing, thank you.
All right, so one last ask for questions, thoughts, ideas, comments. Okay, well, thank everybody for being here. Thank you, Rob. Thank you, Dan.
Eugene, I would like to say something.
Yeah, go ahead.
I would just like to encourage anyone, even if you think you don't have a very good question, I promise you it probably is a good question. Send it to Eugene. I'm telling you,
Gee, thanks.
Robert and
Blow my
Dan
email
have
up.
billion-dollar They have billion dollar technologies, and they're both in their infancy.
In the
All right. Well, thank you for that, Brian.
in the
Okay. So everybody that had put something in the chat or had something to say, we will be, I'll be reaching out to you with emails to set up follow-on conversations with the presenters. I will be in attendance at those first conversations as well. And if anybody has any questions, comments, please feel free to email me. You can share this. Usually takes me about a week to get this up on the YouTube channel. There were some conversations in the beginning that I had with Dan that I have to edit out before I put it up on the document repository. We got into some politics, and I don't like to discuss politics on these. So, thank you all for being here. Appreciate it.
No,
I hope
thank you.
Hope everybody got something out of this, and see you hopefully next week. And for the people that are still here, the invitation for that be coming out tomorrow, and it's going to be AI focused next week's. So thank you much.
Thanks for having us, Eugene.
Okay.
Really
Yep.
appreciate it.
Thanks for being here. Thanks for the presentations. And Rob will have to get you some into PowerPoint for some slides. You're pretty, but the slides.
Well, I don't know for what this is. You know, if I'd showed, for example, here, it's just us here. You know, if I'd showed like an image of this octagonal thing, would that really help people? You know, I mean,
These are scientists and engineers. These are scientists and engineers, and
now you get it. I should have shown. And here it is on top of one of those. Sort of my fingers. There it is. Okay.
There we go. Oh my goodness.
There you go.
Yeah, see now that makes all the sense in the world. Yeah, exactly. Makes all the sense in the world.
Here's pulses. You know, here's pulses. Here's a constellation pattern. But you know, does that really do a lot for your brain? Maybe. I don't know. I mean, people
Picture's
can look
worth
at the
1,000 words
and figure it out. You know.
You're a perfect example. You're trying to get a picture's worth 1,000 words, so you can send one picture that has 1,000 words with optical processing. So
I should have done that, right? But
yeah.
I'll give you the patents, and you can have people look at the patents, and they can look at the pictures, and
we'll figure out how to do this, because this is the first time we did something that was really patent focused, that wasn't a product or you know where you're actually not looking to turn it into a product. You're actually looking to find other people to do it. So
I mean, it's the software to run it. So
this was a new one for us, and I don't think I did it justice. I think we got a lot of good information out there. But
so
we learn as we go.
You can send it out. You know,
sounds good.
And Dan, I've got 2 old patents I did. I'll send you if I can get your email, and it has to do with what you're working on, that area. And I think you'd get a kick out of it, because there was a man named Su-Hang Wu who was an expert on surface phenomena who helped me with the patent. And he's got a bunch of formulas in there, things you probably know about, but he had worked for DuPont. And I think he wrote, he's passed away. I think he wrote like an introduction to in the chemistry book, one that you would probably be familiar with. And so I'll send you some stuff, and you might see an application there, but you'll see some theory from a guy who, at the time, he was one of the top guys in the country when he did his work for DuPont. Anyway, looks like I got some kind of WinZip offer here on my computer. So I'm going to sign off and thank you, everybody. Right. But I'll get you a couple patents that deal with surface energies and contact angles and all that kind of stuff. Had to do with footwear, but
let's
do with a lot of things.
Let's connect.
Thanks very much.
Early next week to get you back on the schedule, Rob, and you too, Dan.
All right.
And think about particulates. If you haven't thought about particulates, Dan. That was a interesting point that Kavita brought up. I'm thinking about, could you keep pollen from sticking to solar panels? or, I don't know. And Kavita, you're still here. So if you want to elaborate, I mean, we're pretty much done. We can do that,
no,
but
similar, along similar lines. I mean, there are many things that are not that don't have any oil or water, but they are pollutants and they do mess up the chemistry of the surfaces. So
okay, I'm happy to get into it. Our professor had an SBIR successfully delivered something to NASA for prevention of moon dust settling on space panels, but let's get.
How do you get the chemical composition for that?
It doesn't really matter.
Moon dust.
Oh, it doesn't. Yeah. Okay,
not so much. No.
Yeah, but I would guess with like pollen, it would be similar to a virus, wouldn't it? I don't know what's your background, Kavita, if you don't mind me asking. Is it medical or?
I'm no. I'm an electronics engineer.
Okay. But yeah, I mean, if you're keeping bacteria, I mean, a pollen would work kind of like a bacteria.
It depends on the self. It depends on what, I don't know. I don't know if everything can. Bacteria may have different. The cell walls are different from what pollen cell walls are. I'm assuming I'm definitely out of my knowledge.
Yeah, exactly. So am I.
Yeah. If I shred the cell wall, then the cell can't reproduce and it's just going to die and not have any effect. So that's the sterilization. But the physical material will still be there. So in a pollen spore, I can't really shred it at the submicron level and have it not do what it does. So we'd have to get into what particulates you want to talk about. I'll share what I know and always tell you what I don't.
And from Kavita, I'm an electrical engineer as well, Kavita, and how do you put UV coatings and hydrophobic coatings on flat panel antennas and be able to because they all interfere with the RF properties. But if you can do this without interfering with the RF properties, or even adding a layer that enhances those properties, maybe even move your lobes around to focus better.
If it can impact the conductivity, and I'm not saying this can make it into superconductors, but it can certainly have other implications, especially
beam focusing and in the phase array. I mean, I can see all kinds of potential for this signatures to reduce RF, infrared, all the different signatures on stuff. I mean, it's and that's why I think we really need to get Dan back on so we can go and cover a lot more of that stuff. And we need to point that out in the next invitation. Go ahead, Brian. You had a question.
Hey, Dan, I'd like to see you touch base again on, even in the next presentation, on how you can use your laser to modify the surfaces between 3D printing passes, or when you're bonding or gluing different materials together, how you might surface etch so that you get a much improved either thermal, electrical, or physical sticky bond between the materials.
Yeah, I'd like to look at acoustic properties too.
We've got a white paper on marine ocean acoustics to see.
Is that something you can share with me?
I can probably share the white paper. It doesn't go into a lot of technical detail, but one of our analysts did a meta study on nanotextures and its potential effect on mitigating underwater acoustics for stationary and marine applications.
Yeah, if you can get ceramics to where they're hydrophobic and not so porous, and still able to conduct or still able to produce, that would be phenomenal. Go ahead, Kavita.
Sorry, just one other question. Dan, do you think your technology can be applicable for cookware?
Oh, yes, definitely. If it's worth it for the vendor, then we can make an omniphobic surface directly on the metal in cookware and not use Teflon. Absolutely, that's the case. But we didn't pursue that so much outside of some commercial applications because the consumer solutions with diamond-like coatings and hexaclad and these other meta surfaces are so cheap, right? It's so much of a solved problem that I'd rather go after the $1 trillion rust problem than making better cookware.
Right.
That's all.
Okay, but from a other than cost, is there any other disadvantage to your technology versus the hexaclad type technology in terms of? I mean, I guess yours could be added on top of those, right? Of those.
Well, for example, if you take, sorry, go on.
I was gonna say I don't think you'd want to, because I mean, one of the problems with Teflon is eventually it does come off and you do consume it, and that's hazardous. So
but I thought the hexaclad, does that have? I mean, I thought this. Maybe I'm confusing myself regarding what hexaclad is, but I thought there's some technology where you're actually not putting Teflon, but you are creating these hexagonal surfaces, and then that's the reason why it's better conducting or something like that.
Well, I don't really know, but if you're going to take a technology that's mass producible like that and sell a $40 pan for $60, it's really just a matter of priorities for us not to have spent a lot of time on it. But we've got a license, and it's in the presentation for an amorphous metal. So if you give me a cheap steel pan and I put 2 microns of amorphous metal on it, it's 10 times stronger than silicon carbide and tougher and more resistant than titanium. I'll nanotexture that, and you have a pan that you can give to your great grandkids. But nobody wants that. Nobody wants nobody wants that kind of thing.
Yeah. Well, something to think about. I'll let you know if I'm planning to start a cookware company.
Okay, I'll be right there.
Yeah, we still live in a disposable economy, so
a little bit, yeah.
All right.
Hey, Dan, this is Brian. My understanding is that your laser system is partially unique because it uses an open air environment and doesn't require a vacuum or shielding gas. And you can relatively do a very large surface area, like a sheet of plywood, in a very quick amount of time.
The rate of work for today is somewhere in the neighborhood of 1 square meter per minute, and we believe that with a little bit of work in the new generation of polygon scanners, we can probably get to about 5 meters squared per minute, which is really, that's faster than most things can paint. So that level of scaling is not something that we worry about so much. But yes, you're right.
Okay. Again, thank you, everybody.